So I am going to talk to you about something called determinants, which you may or may not have heard of before. Did we talk about determinants just a little bit, maybe? I'm not sure, but anyway. So determinants. But before I can do that, I want to go back in time to something simpler. So I'm going to show you a system of equations that this is something like what you've seen in your past. Okay, so we have a linear equation there in two variables, and here's another one. Okay, so what we're going to do is we're going to solve this system and see what happens. All right, now there's lots of ways to solve these systems. One thing you could do is maybe take this, take maybe the bottom equation, for example, and try and solve for y and sub it into the top. It's called solving by substitution. The other way is to sort of maybe see if we can get the coefficients to cancel on one of the variables, get rid of it that way. So maybe we'll try that. I'm going to take the top equation. I'm going to multiply through by c, and the bottom equation, and multiply through by a. If I do that, here's what we get. We can write the c times a times x, or a times c times x. So I'm going to write it that way. Plus c times b times y, or bcy. I guess I'll write it. I'll write it in special order here. You'll see why in a minute. Equals ce. And then on the bottom equation would become acx plus a dy equals af. All right. So multiply through by c. Okay. So what now? Well, you can subtract these, and things are going to be nice because when you subtract them, these cancel, and what do you get? Well, you get bcy minus ady equals ce minus af. All right, we're surprisingly close. We almost have y by itself, don't we? Right? Just a little bit more work here. We can factor out the y. This is y both in locations. So y times bc minus ad equals ce minus af. All right. And then finally, we have y alone. So y is going to be ce minus af over bc minus ad. Okay. So what have we yielded? We have yielded a formula for y if you have a system of equations that looks like the thing up here. Let me put a blue box around it. So if you have this system of equations, the green box has what y would equal. So back in your algebra classes in 9th grade or 8th grade, it would have been nice if someone told you that. Right? You didn't have to do all that elimination stuff. You could have just plugged in these numbers here and got y back. Okay. So what? This doesn't sound like, you said you were going to talk about determinants and matrices. This doesn't look, I don't even know what a matrix is necessarily. You might not be feeling that way. You might think, I don't know what a determinant is. What does it have to do with the following? All right, so what I'm going to do is I'm going to actually just show you what a matrix is. A matrix is simply a set of numbers laid out in a rectangular array. So a matrix might look like this. A, B, C, D. Right? So that's our matrix. And typically, usually you put brackets around it, maybe, or something. But if you write a matrix like this, A, B, C, D, and you put vertical lines on it, like that, instead of the brackets, then this means find the determinant of the matrix. Okay. So the determinant has a definition. Here's what it is. You're going to say, okay, I accept this definition. The determinant of a matrix is the product of these two numbers, A times D, minus the product of those two numbers, B times C. That's the determinant of a matrix. Or I should say of this matrix. This is called a 2-by-2 matrix. Okay? The reason it's called a 2-by-2 matrix is because it has 2 rows and 2 columns. Okay? Usually that's the number of rows, and that's the number of columns. So that's how you denote it, a 2 by 2 matrix. Okay? All right. So the next question is, what does this have to do with our system of equations that we solved? So let's just keep that in mind. Keep this fact in mind here that we just found a determinant of a 2 by 2 matrix. Let's go back and look at this page and look at our solution for y. Okay? And if you notice, if you look at the numerator and denominators of these fractions, right? Let's just change things a little bit. Maybe it'll become a little nicer. So I'm going to take this. I'm going to say, all right, y equals, and I'm going to change the order of subtraction on the numerator. So I'm going to make this AF minus CE. Okay, now it's okay for me to do that as long as I do the same thing on the bottom. You give that a little bit of thought, you realize, here's what I did. I multiplied the top and bottom of this expression by -1. And if I do it to the top and bottom, then really I've multiplied the whole fraction by 1. I haven't changed it at all. Okay, so now, okay, pause for a minute and ask yourself, hey, where have I seen that before? Think back, maybe 2 minutes, not even, right? And that is the determinant of this matrix. A, B, C, D. That's the determinant of that matrix. Okay? As according to our definition I just gave you on the other page. There it is. A, B, C, D as that determinant. Okay. So then what you should try and do is fill in what matrix goes there so that you end up with this determinant. So we have A, C, E, F. So there you go. All right. So you can actually write the solution for y to a system of equations as the quotient of 2 determinants. Okay. I'm just going to do one more thing just to ask you this question. Would this also equal the following? A, C, E, F. Take a look at that numerator, that matrix, and ask yourself, is the determinant of that matrix the same as the determinant of this matrix? B, the answer is yes, because up here you would do, let's use different colors, you do A times F, just like you do A times F here, and then you subtract E times C or C times E. Now, there's a reason why I decided to just, this is called transposing matrix. We won't worry about that language yet, but I sort of flipped it about this line here down the middle. I sort of flipped the matrix that way because I want to look at that matrix for a minute and compare it to the original system. So let's make a note here. Ready? It's A, C, E, F over A, B. Oh, my bad. Sorry. A, B, C, D. And this was equal to y. And that's true when our original system is this. Okay. So if this is our original system of equations, this is the y value that we yield. So if we look carefully, we can see where, for example, this matrix on the bottom comes from. Look at all those little numbers. Do you see them in the original system? They're right here. They're the coefficients of x and y. Alrighty. Now, this is a little tougher to see. Let's look at the matrix on top and ask yourself, where could we have gotten that matrix from? Okay. This matrix, these blue numbers here up top here that I've underlined are not the matrix of coefficients of x and y. So something got changed. You want to think about it this way. This will help you a little bit. Here are the coefficients of x. These were the coefficients of y. And if we look at the upper matrix, these are still the coefficients of x. But the coefficients of y are gone, and they've been replaced with, I need another color, I guess we'll just go back to a little blue. They've been replaced with these. These have taken the place of where the y coefficients used to be. Okay? So I'll underline in blue, there's where that upper matrix comes from. So what you've done is, really, in the numerator, you took the matrix of coefficients, and you took the coefficients that used to be on y, and you replaced them with these numbers e and f over here, which I'm going to call the answers to the system. Right? Not the actual answers for x and y, but what the two equations equaled. This idea works now. So if you wanted to find x, if you do all the algebra, and you're just going to have to trust me on this, unless you really want to do it on yourself, in which case you can pause and do that. The denominator would still be the same, a, c, b, d. But in the matrix on top, we would take what used to be the x coefficients, which were a and c, and replace them with e and f. So it would be e, f. This is where x used to be, bear in mind. And since we're not solving for y, these would say b, d. All right, so you can use determinants to solve systems of equations. This process, by the way, has a special name. It's called Cramer's rule, which you may have heard of in the past. So you would think then that, maybe this idea, where you say, well, isn't this idea extendable? Like, for example, suppose I had this system of equations, ax plus by plus c times z, and then ex plus fy, well, I'm sorry, not plus, yeah, plus fgz, remember my alphabet while I'm doing this, gh, so hx plus iy, now be careful, that is not the vector I, that's just I number, ij, so j, z equals k, l, m, right? I skipped D, didn't I? I did skip D. Well, that's all right. It doesn't matter. All right. So, yeah, maybe I skipped D on the paper, but I didn't skip D because I'm writing it. I am D. So D is a part of this problem, no matter what you do. And you can all hear that, right? Okay. So it turns out this Cramer's rule is extendable. So you can actually write down what x is right away. So let's just be careful. So x is going to equal. All right? So the bottom matrix is sort of easier to know. It's just the matrix of the coefficients of all the variables, x, y, and z. So here we go. Ready? A, B, C, E, F, G, H, I, I, J. Okay. And that's the determinant of the matrix of coefficients. In the numerator, here's where we have to be a little careful. We think about how we used Cramer's rule in the previous problem. What we're going to do is we're going to take these guys, KLM, and replace the coefficients on the x terms with that KLM. So it'll be KLM, which will be here, but then this will be B, C, F, G, and I, J. Okay, great. No problem. So all I have to do is find those determinants. If I find a determinant of the numerator and denominator, I can divide them. I know what x is. There's only one problem. We didn't talk about how to find a determinant of a 3 by 3 matrix. So now we need to go do that. We need to work out this determinant of a 3 by 3. So here's what we're going to do. A, B, C, E, F, G, H, I, J. Okay, so that's sort of a strange thing. I'm leaving D out again, but I'm really not. I'm writing it, but whatever. Okay, so here's the question I want you to think about, or the claim I'm going to make. I'm going to say to you, I claim that for any element of this matrix, so if you pick A, or you pick F, or you pick G, any one of them, that once you pick one of these elements, that you're automatically determining a 2 by 2 matrix. Here's what I mean. I'm just going to copy this for a second so that I have it for a little, to try to show this again. But let's say you pick the element A here. Element A is in the first row and first column. So what I'm going to do is I'm going to cross out the first row and cross out the first column. And then what do you notice here? Oh, wow, a 2 by 2 matrix. Okay? And you can play this game with every point. So, for example, let's do this. Let's pick the element F. You pick the element F. It is in the second column, second row. And here you have it. There's a minor. I'm actually not going to use that language yet, but there's a matrix, A, C, H, J, that goes with F. That's sort of the minor of that element. That's what we call it, actually. So when you have an element, you cross out the row and column it's in. The matrix that's left behind is called the minor of that element. Okay? Just for fun, try one more. Let's find the minor of the element G. So we cross out that second row and the third column, and we get A, B, H, I. Now, that's sort of promising. We kind of like seeing these small matrices, these 2 by 2 matrices, because we know how to find the determinants of them, correct? So we're happy about that. We can get the determinant of this matrix, of this little guy. Just how do you put it all together into one big thing? So that's what we're going to do to finish off here. All right? So here's how you do things. You start with the first. You could do any row, actually. I'm going to use the first row here. I'm going to start with the element A. And that element A I'm going to write here. And I'm going to multiply that by its minor, which would be F, G, I, J. So I started this process by taking A and multiplying it by its minor. Okay. Here's the part that's going to be a little less obvious. You'll see in a minute. Next, I'm going to move to the element B. I'm going to do minus B times its minor. Now, the minor for B would be E, G, H, J. Agreed? All right. And then lastly, pick a different color. I'm going to take the element C here. I'm going to do plus C times E, F, H, I. Okay. So that would be the determinant of this matrix. The only question I would expect you to be thinking about right now is, how come that B has a minus in front of it and the A and the C do not? Okay. And I didn't write this, but you can think of it this way. Really, in front of all of these pieces that we're adding and subtracting together is this factor, -1 to the R plus C, where R equals the row number and C equals the column number. So if we think about this just for a moment, A, the element A here, is in the first row. Right, here it is, it's in the first row, and it's in the first column. So that means that there's really in front of here the following. It's -1 to the 1 plus 1 power. That's -1 squared, which is +1. I'm not saying why this factor appears here. I'm just telling you that it's there, really. You go over here, there's really a -1 times the, well, let's see, B is in the first row, but the second column. So that's -1 to the third power, which would be -1. Okay? Now, before you get all nervous or anything like that and think, oh, I'm going to do -1 to the R plus C all the time, just think about the pattern of signs, S-I-G-Ns, that is. Look, the first one's going to be positive. That's going to be negative. That's going to be positive. Then you go to the next row. E is in the second row, first column, which is 2 plus 1, so that's negative again. F is in the second row, second column, 2 plus 2 is 4. That's going to be positive again, negative, positive, negative, positive. So you get this checkerboard of pluses and minuses that you can lay down on top of your matrix. So if you think about it that way, like a checkerboard, it's probably easier than worrying about this factor I wrote, -1 to the R plus C power. Okay. Now, let's take this thing here, and let's go actually write it out. Okay. Edit, paste it. There it is. So I'll get rid of this part for the time being. We won't worry about that anymore. All right. Let's actually write out what this thing equals. I'm just going to use all one color. So this is going to be A times Fj minus GI minus B times EJ minus GH plus C times EI minus FH. So let's just finish this off. I'm just going to distribute the A into these things. So I get AFJ minus AGI minus BEJ minus, or plus I should say, BGH plus CEI minus CFH. Okay, so we've got that. That's our determinant. If you want now, you can memorize this as the way to get the determinant. Or you could just know this process. Okay, this process, by the way, is called expansion by minors. Okay, and here's sort of a fun thing. You have options. Okay, this is called expansion by minors. If you look back at the matrix, I expanded using the minors of the first row. I looked at the first row, I went across A, B, C, and I wrote the determinant that way. Well, it turns out you could expand by the minors of any row or column. So let me show you what I mean here. Let's go to this thing. We'll write the matrix again. A, B, C, E, F, G, H, I, J. That's supposed to be a G. Okay, so instead what you can do is we can expand by a different row. So maybe we want to expand by the minors of the last row. Okay, so let's remember our checkerboards of plus minus, right? This is going to be plus, minus, plus, minus, minus, plus, minus, plus, minus, plus. Here we go. Ready? It's going to be H, it's positive H because the plus here, times its minor. Now, its minor, the minor of H would be B, C, F, G. It's this matrix up here. Okay? Minus I times its minor, which would be A, C, E, G. And then lastly, plus J times its minor, which is going to be A, B, E, F. Okay. So go ahead and take a minute and try and reduce that. So if we finish this off, this is going to be H times BG, BG minus CF minus I times AG minus EC plus J times AF minus EB. Okay, so what does this turn out to be? HBG minus HCF minus IAY plus IEC. Sorry, I meant to say G. That's a G there. Okay, plus JAF minus JEB. So here's another way, another thing you can remember to get the determinant. But if you look carefully at this expression and this expression, we'll copy it, and we'll go to this page, and we'll paste it. We'll bring it down in pieces. There you go. And then this piece, oh, not that. This piece. No, come on. This piece. There we go. If you look carefully at the black box and the blue box, you can find everything that matches. Here you go. That matches, right? This matches. Here we go. This and this match. This and this match. And we're getting there. That and that. And hopefully, yes, it does. So it doesn't matter what row you expand by minors with. And you might say, well, why would you care? Why wouldn't you just memorize one of these? Well, sometimes your matrix, if you look at your original matrix, it might be the case. Let's go back to one down here. Maybe in the middle of your matrix, or maybe right here, this F was a 0. So if the F were a 0, then I would advise expanding by that row. because it would kill one of the terms. Not to be brutal, but the middle term here would go away. It wouldn't be there. So there you go. That's the process of expanding by minors to find determinants.